I think I combined these two, but so what if we don't combine them? What's the difference? So this is if we start just directly from here, or we can combine two items over here, which is AB or A or B, C inverted. So if we directly draw the schematic from here, these are AND logic, and in between them are ORs. So expecting, you know, 1 block, 2 blocks, 3 blocks. On the top for the PMOS, they should be in series because that's the OR logic. You have to think about the NOR gate, right? NOR gate. But it's an AND logic inside the block, so they need to be in parallel, okay, for the PMOS, and these are in series. So it's going to be AB, AC, BC. So for PMOS, when you're looking at it, so if you have AND logic, just put them in parallel. Okay, AB in parallel, AC in parallel, and BC in parallel. And if you see OR logic, you place them in series for the PMOS. And then for the NMOSes, it's an OR logic for these blocks. So they should be in parallel for the NMOSes for these blocks. And within each block, it should be in series for the NMOS. Now let's draw the stick diagram of it. See if this is easy. This becomes 6 transistors. So you need 7 nodes. I'm not sure if it's possible. Let's just try it. Okay. Two in parallel is pretty simple, right? But after the 2 parallel transistors, you need to directly connect to the next one because they are in series. So would you prefer big 2 transistors in parallel? You can connect in multiple ways, right? You can do this. That's the first way to do it, or you can do this, right? So for something, you have a lot of things next to it or below it. You have to place them in series, which one you want to use and why. No. Because in this case, you have a lot of transistors on the other side, right? If you have the output in the middle, then the output is not directly connecting to anything. You cannot connect this one to anything else. Because you have something already connect to this one already in the line, right? It's not just 2. You have 7 or 6 transistors in the line. So they're already connected.
Oh, if you're putting another
no, you have parallel transistors, they are in series, right? Yeah. And they're already connected here. So which means you have to use this one to connect them together. So if you are, for example, these two transistors are in parallel, right? And this must be the output because in the one liner, it's already make the connection. You cannot change it. It's already made the connection in the line. Did you get that? So if you do it this way, you are trying to use the output, use the middle node as the output. However, the node on the side is already connected to the next one, the next transistor. You know what I mean? Does that make sense? So we have to do it this way. Okay? So the output can be the one already connected to the next one. So we can directly use it instead of use the middle one, which doesn't have any connection, direct connection to the next transistor in series, put in series in the circuit. So one line comes from the power supply and getting split into two branches and merges into one node. It's just one wire, it's one node, right? So this node is this node. And this is connected to the drain, the sources of the two PMOSs over here, already in the line, since I just drew a one line to make it easy to lay out. Okay, that's why we want to utilize this one and use it as the output of the first two PMOS transistors. What about next? Can we do it one more time? Is that still possible to have three parallel PMOSs in series? So we have the output here. Can we still do it? So this line, this output already, you cannot have another choice because it's already in the line, right? So this output already inject the current into one of the nodes, for example, one of the transistors already. And now you have to split it. So if we split it this way, then we got a middle transistor which cannot be connected to the next. It's going to be an issue like this one. Can we do it a different way? So this current is going to flow through this transistor and reach here, right? And we need another transistor in parallel with this one. And how can we do it? Can we route it here? Like from here to here, then the output becomes this one. Then we have to short them together. And seems like it's going to work. Because we cannot do it this way, right? Can we? It's not going to work because we got a middle transistor here. It's not going to work. So let's try it. I don't know. Let's do it this way. Okay. So we got a one transistor and two transistor, and then it merges into one node, and I have to short these two in order to make these two transistors in parallel. Right. So that becomes the output. It's not going to work. No. It's not working. Is that still possible? Maybe like three in a row and work for a one-liner here. Probably haven't done that in the past. Hmm. Yeah, I've never done that in the past. So possibly it's just impossible. Mhm. Let's try it one more time and see. So what about the endmost? Let's see. Try the easier one first. Is endmost easier? For example, there's you can get output from the top, and it's just three. Yeah, I think that's doable, right? Like this. Yes, right. Output current flows in here and runs through these two transistors, go to the ground, and these two transistors merge to the ground, and these two transistors merge to the ground. So just two in series and in parallel with these two and these two. The NMOSes are always simple, easier than the PMOSes. I don't know why. But now let's come back to the PMOS and see if we can really figure that out. Let's try it in a different way. Two in parallel. Can we start in the middle instead of from the side? If we start in the middle, then probably not, because it's making connection from here to both of these two parallel transistors, and it shouldn't. Right? Because they don't have a common connection in between them. Let's try it one more time. This one, are you also trying on your side? From here, we have to split it. I think it's just impossible. Okay? So that's why we want to combine it first. Simplify the logic first. So for this one, how many transistors? 3. Let's start with the schematic first. So LI logic, AB on the top for PMOSes, there should be in parallel, right? And OR logic, will place this in series with this one. So you need A, B in series, and parallel with C, and make the connection like this. So for NMOSes, A, B are in series, and or it's a NOR gate, so the NMOSes are, so these and these are in parallel, right? These are in series, so it's going to be AB and C. That's a schematic. 1, 2, 3, 4, 5. Two in parallel first, same concept. And then it's basically two in parallel as well, but this is just a two in series. You just need a two transistor in a row. So this is sort of easy to handle, right? How to do it? It is one transistor in parallel with the two transistors in series, right? So for example, from this node, this node already has two transistors, right? Flows through here, so you just ground it. No, you just use this node as the output. I got another one from the other side, right? So that's easy. Now you have AB in series, go to ground, just do this, right? So AB in series goes to ground. And then AB in parallel, and then connect to C. Would that be easy to do? Seems like we're seeing the same problem again, right? Like this. If you have two parallel transistors and followed by we're having another transistor or two transistors in series with that parallel transistor, you don't want the output of the parallel transistor to be in the middle for the one-liner, right? Same thing here. So now we have to figure out how do we do this one, okay? And now the output is, or the shared joint is over here. It's already in the one-liner. It already has a connection to the left and to the right. So you can have no choice, right? So how to make a parallel transistor? So if you have something here already, seems like you have to merge it in the middle to form a parallel transistor. And in that case, you've got a middle transistor, which is not able to reach C here. What's the solution to this issue? So this one is being split into two ways, right? And flows through this transistor, and if we connect here, then it's going to flow through this way and merge in the middle. Okay. The problem is this node already made a connection to C. However, you are trying to use this one as this node. It's a dilemma, right? What's the solution to it? The original schematic, how do we redraw it? That's right, yes. Just swap these C and A and B in parallel, right? So replace this guy with okay. So in that case, what we can do is right after this output, okay, we don't use this anymore, okay? So this can be used as C, and then the output reaches here from C. We just drew a parallel transistor for A and B like that. Okay. That is because we have this output connect to the middle at the very beginning. Do we have a different solution to this drawing here? Let's try it. I'm not sure yet, but let's see what's going to happen. So for example, output comes from here, right? Can we, which one, this one?
Yeah.
So use this one as C?
No.
Oh, like this?
Yeah.
That's C? So that will be C, right? And then this, right? No. No. Wait, so this is AB in parallel, right?
Yeah.
And then this must be C, right?
Yeah.
And then this one series. Oh, like here, right? Yeah, that's another solution. Exactly. They're ready for the quiz. Make sense? Let's see. For example. You'll see the benefit of combining the logic or simplifying the logic expression first. Let's look into adders real quick. The first one is called ripple carry adder, which is the most common one. Ripple carry RCA. And the logic is for the full adder, this is the full adder design. You have three inputs. This is carry in, and you have a summation and carry out. These are all the possible inputs. Okay. And this is 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1. Okay. To recap on the logic design, how to design a circuit out of this logic. This is what we want, right? It's the desired results. Inputs, outputs already defined. Okay. Now we need to design a circuit, hardware, to implement this logic. Whenever you give the inputs in here, you should receive these outputs, and then we can call it RCA. So now we have the desired input and output. What's the next step to design a circuit with the connections to the circuit? So first, is this really simple logic that we can really just eyeball and then draw the schematic? It's very difficult to make the connection from this to the circuit, okay? Because the circuit is really the final product that you can use. You can plug into the power supply and measure the output. It can be used eventually. It's called K-map. So first, let's look into S. You have to deal with each input once at a time. So let's look at S first. So just ignore CO. And the inputs are A and B, C, I. It doesn't matter how to combine them. It can be A, B, C, I, it can be A, B, C, I, either way. For A, you have 0 and 1, two possible inputs. And for BCI, it's going to be 0, 0, 0, 1. Make sure you're only flipping one bit each time. So it's 1, 1 or 1, 1, 0 here. Okay. Then see what are the locations of the ones. Have 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, and 1, 0, 0, and 1, 1, 1. Okay. We are trying to simplify it using a K-map, but it cannot because they're not next to each other, pretty apart away. So you circle them and find out you cannot combine anything. All right. So eventually, this becomes you just directly write them down. Okay, S equals. What are they? Just to remember how to write it down by looking at the ones. This is A naught because there's a 0 here, right? A naught, B naught, and CI. Or A naught, B, CI naught. Or A, B naught, CI naught. Or A, B, CI. Because if you cannot simplify on the K-map, you won't be able to simplify over here as well. But we can combine them, right? At least, and see what we can get from here. So this, if we take factor out CI naught first and CI for these terms, so we can get A naught, B naught, or AB, CI, or combine these two terms, it's A naught B or AB naught, CI naught, right? Okay, and you can find out this is XNOR, this is XOR. And we derived on Wednesday that the XNOR is the inverse of XOR, vice versa, right? So what you can do is, let's just use XOR for example, and this is XNOR. So this becomes A naught B or A B naught, which is XOR not, okay, which is XNOR. This is the inverse of this, right? Then CI or A naught B or A B naught, CI naught. Very interestingly, if you treat the AB XOR as one entity, right? And this is another XOR logic. See, this thing not CI or this thing CI not. So that's another XOR logic. So eventually you are getting A XOR B XOR CI. Is the logic getting simplified? No. It just saves some ink. It's not saving any circuit or on the chip. I'm just using a symbol to represent everything here. It's not changing anything. Only changes when you write it down on the paper. If you implement it on the circuit, it's not changing anything. Mm-hmm. It's just for this circuit because on the K-map, you cannot combine anything and simplify it. But actually, it's partially right because, let me see. It's really not necessarily changing anything, but it may make it easier to lay it out by using the AOI logic. The reason that this is not simplifiable because it's by the nature here, right? If you look at the K-map, you cannot combine anything and simplify it here. The reason we use this one to represent it is because this gate, okay, it's called XOR gate, right? It looks like just one gate. However, in the XOR gate, you have a lot of AND and ORs and inverters. So what is the XOR logic? It's A not B or A B not, right? So if you draw it just using the gates, this looks like one gate, but actually in the circuit, it's not one gate, right? You have A, B, the two signals, right? And this is A naught, this is B naught. So it must be A and B, no, A naught and B, or A and B naught, and then OR. So this is one gate, same as this gate. It just looks simpler, but actually it's not on the chip, on the physical chip. The reason you cannot simplify is because of nature here in the K-map. There, you don't have neighboring components that can combine them and simplify it. They're all independent ones, right? So, but eventually, if you use the AOI logic instead of using the independent gates to directly just build it through the logic, if you use AOI logic, it may simplify the transistor level circuit a little bit, but won't be, significantly reducing the number of transistors from here to the AOI logic. You could even draw AOI logic from here, can you? If I'm asking you to draw a schematic, the transistor level schematic from here, how would you do it? Like these ones. See? For this simple thing, we already spent so much time on it, like 20 or 30 minutes in the class. What about this one? What have you do? You just have to put two bars on the top, right? And then do millions of De Morgan's law, remove the bar, split the bar, change the sign, and then keep doing that for many times in order to simplify it, right? Okay, it's not that easy, but eventually we'll be able to find the transistor level by combining some of the terms and reusing CI. I'm going to show you the equation really quick. It's kind of like a conclusion from the textbook because it's not that repeatable. Some of the simplifications, it's not that easy to find out. It's just an experiential conclusion, I think, from someone. So that's for S. What about CI? Or CO, sorry, CO. Again, we still have to start with the K-map. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. 0, 1, 1. 1, 0, 1. 1, 1, 0. 1, 1, 1. Looks better. So we can do this, can do this, can do this. Okay, so for these two, A is 1, so it's not being flipped. So you only cancel the one the bit is getting flipped, which is this guy, right? So CI, because for the CI position is always 1. So the first one is ACI. And here the second one is AB. And these two, A is getting flipped, so A is canceled. So it becomes BCI. So this is eventually A or B, CI or AB. Okay, it's a lot easier, a lot easier. We can simplify it because on the K map you have neighboring components. You can combine them together. And for the logic, the first one, you know, when in the textbook, right? So when this is getting converted to a version that is considered easier for the AI logic, so what that how we do it? Okay, so first we should write this down for S. Okay, A not B or AB not X or CI, right? Mm-hmm. And this equals A or A not B or A B not. We just expand it, right? Expand it. So this becomes CI not or A not B or A B not CI. It's gonna be really tedious, and you don't need to know how to do it. I'm gonna directly show you the conclusion here in a bit. So this one, and then you just keep doing it. Eventually, it becomes something I'm going to show you on Monday, I believe. And then we will find out the schematic and layout from that logic expression on Monday. So Tuesday, I think you guys are going to lay it out next week in the lab, right? Okay.